Hi, welcome to one of the most useful statistical rules of thumb in everyday life, Part 1. Okay, so let's say you run a business that sells some product. You ship your product to your customers. Sometimes it breaks en route, and you have to give them a refund or send them a replacement. If you could reduce the rate of breakage by 10%, you could use the money to buy more advertising. Now, a friend of yours in a very similar business says that they recently changed to using a new type of packaging. They say that the change has reduced the rate of breakage in their shipments by 20%. You inquire further. So your friend says the following. Historically, we've had, on average, 25 units break per month. We switched packaging a month ago. Since then, we've had 20 units break. That's a 20% reduction with the new packaging. So I think it's a big improvement. Okay, so here's our question. How compelling is your friend's suggestion to change the packing material? Okay, so the topic of this video is why it's useful in everyday life to know the standard deviation of the Poisson distribution. Here, we're just going to concentrate on some practical use of the standard deviation sigma of the Poisson distribution. We will do slightly more complicated cases in Part 2. Now, there is some background information that would be useful in order to understand this video. So you might want to check out the video, Why the Poisson Distribution is Important. It's Everywhere. So in that video, we give an introduction to the Poisson distribution, and we discuss when the Poisson distribution applies. You might also want to check out the video, Mean and Standard Deviation of the Poisson distribution. So there we derive the standard deviation sigma of the Poisson distribution. And you might also be interested in other videos in the Poisson Statistics playlist. Okay, first let's give a very quick review of the Poisson distribution. Okay, so let's say we have some event which, 1, occurs randomly, but whose probability of occurring per unit time is constant, and 2, where the occurrences of the event are independent. Now, this rate of the event occurring is independent of how many times the event has occurred before or when the event occurred before. So let's call that rate R. So some possible examples of R are 5.7 per minute, or 3.7 per year, etc. Next, let's take a time interval, which we're going to call T. We're going to define the quantity lambda to be R times T. So on average, over a time interval T, the event will occur lambda times. When you observe for a given time interval T, the actual number of times you see the event occur is a quantity which we're going to call M. And the Poisson distribution, which we write as P of M given lambda, gives the probability of observing each possible value of M. So P of M given lambda is equal to lambda to the M, e to the minus lambda over M factorial. Okay, next, the standard deviation sigma of the Poisson distribution is the square root of lambda. And sigma quantifies how much M typically differs from lambda. So for example, if lambda is equal to 100, M will typically deviate from 100 by about 10. So observations of M equals 90 or M equals 110, or really anything in between, would be fairly ordinary outcomes. Okay, back to the example. Okay, so let's remind ourselves of what your friend said. So they said the following. Historically, we've had, on average, 25 units break per month. We switched packaging a month ago. Since then, we've had 20 units break. That's a 20% reduction with the new packaging, so I think it's a big improvement. So here's the question that we'll ask here. If your friend's broken shipments follow a Poisson distribution with lambda equal to 25, is having only 20 shipments break in the last month all that unusual? But before we ask that, we should ask ourselves a couple of more basic questions. So first, is the Poisson distribution even appropriate for this example? So the Poisson distribution would require the following. It would require that the probability of a shipment breaking per unit time is constant, and it would also require that the probability per unit time of a shipment breaking is independent of whether or not other shipments break or when they break. So are these requirements fulfilled? Okay, so first let's ask, is the probability of a shipment breaking per unit time constant? And here are some questions that we could ask ourselves in order to answer that question. So for example, is the rate at which shipments are sent out constant? Have there been any changes to the shipping protocol? Are there any seasonal effects which affect the quality of shipping? And so on. And now for the second question, is the probability per unit time of a given shipment breaking independent of whether or not other shipments break? So for example, one question we might ask ourselves is, are the shipments sent out separately on separate vehicles? Okay, so here we're going to assume that the details of your friend's shipping situation are such that a Poisson distribution would be a reasonable description of their broken shipments. It's important to know when the Poisson distribution applies and when it doesn't. So if you'd like an example of when it doesn't apply, you might want to check out the video, Are YouTube Views Poisson-Distributed? Okay, so now let's get back to the question. If your friend's broken shipments follow a Poisson distribution with lambda equal to 25, is having only 20 shipments break in the last month all that unusual? So here, lambda is equal to 25, and sigma is the square root of lambda, so that's 5. So an observed value m that differs from lambda, which is 25, by sigma, which is 5, or less, would be actually very ordinary. So if the rate of shipment breakage did not change when your friend switched to a new type of packing material, this value of m equals 20, is actually quite reasonable. So the evidence for your friend's assertion that the new packaging improved the breakage rate isn't great. Now, we should mention that this does not mean that your friend is wrong. So this is one of those cases where it's important to point out that absence of evidence does not equal evidence of absence. But there isn't strong evidence to indicate that your friend is right. Okay, so in part 2, we'll talk about some more statements that we can make in the case that lambda is large. So for large lambda, the Poisson distribution approaches a Gaussian or normal distribution. And in the limit where the Gaussian distribution is correct, m will fall in the range between lambda minus the square root of lambda and lambda plus the square root of lambda about 68% of the time. We'll talk about this and other useful results in part 2. Okay, so let's briefly summarize. So here we've looked at an example that demonstrates that it can be useful to know the standard deviation of the Poisson distribution in real-life scenarios. The example here was one where the observed value m of broken shipments was 1 sigma smaller than the expected lambda. We'll look at slightly more complicated examples in part 2.